Hello, stat students. So yesterday we talked about percentiles, density curves, transformations, and z-scores. But today we'll be talking more about density curves and a special type of density curve. But before we go into that special type of curve, let's talk about density curves in general. I've mentioned that you should draw it over your graph so you can kind of see the skewness or if it's symmetric. So in chapter 1, we developed a guideline for analyzing quantitative data. We graphed our data, so it was dot plot, stem plot, histogram, a box plot, whatever. We analyzed the distribution, shape, center, spread, outliers, the SOCs. We calculated the numerical summaries. Now we add a fourth thing. Sometimes the overall pattern of a large distribution is so regular that it can be described by a smooth curve. This curve is called a density curve. A density curve will always be on or above the horizontal axis. A density curve will always have an area of 1 below it. Density curves come in many shapes and will describe the overall pattern of a distribution. No set of data is described exactly by the density curve. It is an approximation that is easy and accurate enough to use in statistics. And there on the right you see a density curve. The mean of a density curve can be found by dividing the area under the curve into two equal areas. I think I said mean, I meant median. So that about 50% is to the left of the median and about 50% is to the right of the median. The mean of a density curve is the balance point of the curve where it would balance if it were made of solid material. So if you look at the diagrams below, the last picture shows the mean as the balance point, and the other two show the mean not as the balance point if we're placed somewhere else. If the distribution is symmetric, the mean and median will be the same. If the distribution is skewed, the mean will be pulled toward the tail or toward the skewness. So if we look at the first picture below, the mean and median are the same. And then if we look at the second picture where the density curve shows right skewness, the mean will be greater than the median. It will be to the right of the median. Okay, one special type of density curve is what is called the normal curve. I capitalized normal to just show that it indeed is a special type of curve, which describes a normal distribution. Normal distributions have special properties, and contrary to their name, they are not normal. In fact, they are unusual. All normal curves are symmetric, single-peaked, and bell-shaped. Most data in real life is skewed and is not normal. All normal or any specific normal curve is completely described by giving its mean mu and the standard deviation sigma. And I think I got a little ahead of myself. So the mean is located in the center of the curve and is the same as the median. Changing the mean without changing the standard deviation just moves the distribution along the horizontal axis. The standard deviation controls the spread of the distribution. The mean and standard deviation, so mu and sigma, define the shape of the normal curve. We should be able to eyeball the curve to determine the standard deviation. The point on the curve where the slope begins to lessen will be the standard deviation. If you took calculus, this would be known as the inflection point, but you don't need to worry about that because you don't need calculus to take this class. So if you haven't taken it, don't worry about it. Normal distributions are good approximations of many kinds of chance outcomes. Many statistical inference procedures are based on normal distributions. And so if you look at both of these diagrams up above, you see the mean right here. And you see the standard deviation because this would be like the inflection point. So it'd be one standard deviation, and there would be 2 and 3, and we'll talk about that in a second. So why are normal distributions important in statistics? Well, there's 3 reasons. First, normal distributions are good descriptions for some distributions of real data, and this would include, for example, scores on tests taken by a lot of people, like the SAT exams or IQ test. And second, normal distributions are good approximations to the results of many kinds of chance outcomes, like I mentioned. And then basically, even though many sets of data follow a normal distribution, many do not. Examples, most income distributions are skewed to the right and are not normal. Some distributions are symmetric, but not normal or even close to normal. So there you have it. So the next thing we're going to talk about is the empirical rule, and you need to memorize these 3 values. You just need to, and that's the bottom of the line. So memorize those 3. Okay. So that is known as the empirical rule. And I teach in algebra too when we do the brief statistics unit. In a normal distribution with mean mu and standard deviation sigma, so remember the mean mu is also known as the population mean, and the sigma is the population standard deviation. 68% of the observations fall within 1 standard deviation. And to note that, you put 1 sigma of the mean. 95% of the observations fall within 2 standard deviations of the mean, and 99.7% of the observations fall within 3 standard deviations of the mean. So if we look over here, this is your mean right here. Or I'm sorry, it's the mean also, but the standard deviation 1, 2, and 3 above the mean would be, this is 1, but this -1 counts as being within 1 standard deviation, so it's to the right and left of the mean. And then you have 2, -2 is 2, and then 3 standard deviations. So this is how it works. So 68% of the data, so here's the mean, if I was to draw this. 68% of the data would fall within 1 standard deviation, so within these 2 bars. So splitting that up, that would be 34% here and 34% there. And that's where you get 68%. For 95%, you just do 95 minus 68, so that's 27. So we have 27% within 2 standard deviations, so all the way from this bar to that bar. So this accounts for 68. Subtracting, we'd have 27%. Split that into 2, and this would be 13.5%. And this would be 13.5%. But as long as you remember the 68, 95, 99.7, you can come up with these numbers. And then lastly, the darker shaded blue would be 99.7 minus 95, and that would be 4.7%. Divide that by 2, and this right here is 2.35%, and this is 2.35%. But take into consideration now all the way from, I'm sorry, that would be the area, but that would be 3 standard deviations from the mean. And lastly, anything beyond that, so this would be the remainder. So at this point we have just whatever's remaining, so that'd be 0.3. So 0.3% would be, so this would be 0.15%, and this would be 0.15% right here. We're only interested in the 3 standard deviations from the mean. And now we're just going to do examples. For the AP exam, if you're asked questions about the normal curve, you must show, this is what side information, my notes, your diagram labeled as showing your work. That relates to this sample problem right here. In a previous example about batting averages for Major League Baseball players in 2009, the mean of the 432 batting averages was 0.261 with a standard deviation of 0.034. Suppose that the distribution is exactly normal with mean 0.261 and standard deviation 0.034. A, sketch a normal density curve for this distribution of batting averages. Label the points that are 1, 2, and 3 standard deviations from the mean. So the first thing we want to do is right here, we want to label the mean. So that would be, and I'm going to go ahead and label it down here so I'm not in the way of the graph. So that would be 0.261. And then the standard deviation is 0.034. So what I do is to this number 0.261, I'm going to add 0.034, and I'm going to get 0.295. Okay, so next one, you're going to add 0.03 for it, and you're going to get 0.329. And then this last one, you're going to add 0.034 again, and you're going to get 0.363. Because anything to the right is standard deviations above the mean, anything to the left is below the mean. To get this value, you're going to take 0.0261 and subtract 0.034, and you're going to get 0.227. This one would be subtracting again, 0.193. And lastly, this one right there would be 0.159. And that's just me subtracting 0.034. All right, so I've sketched the picture. Now I can answer the questions based on my diagram. I would do one more thing and go above and beyond here, is I would label this 34%. This is 34%. And then this would be 13.5, 13.5, 2.35, 2.35. Do you need to? Not necessarily, as long as you remember the 68, 95, 99.7 rule. What percent of the batting averages are above 0.329? So here's 0.329. So it would be anything above, so it would be anything to the right. So you are going to add 2.35% plus 0.15%, and that'll give you 2.5%. Hopefully you remember doing this in the past. What percent of the batting averages are between 0.227 and 0.295? So let's see. And if you look at that, that's one standard deviation within the mean, so that would be 68%. And that's how you analyze a normal curve. Let's do a few more examples. Okay. And before we do a few more, let's talk about the standard normal distribution. A normal distribution where the mean is 0 and the standard deviation is 1 is called a standard normal distribution. Just a little smaller. Every value in this distribution has been translated into a standardized score. So remember we talked about standardized scores as z-scores. Okay. And so if you look over here, these are your z-scores corresponding to this density curve. So you have 0, 1, 2, 3, 0 being your mean, and then 1, 2, 3 standard deviations, and -1, -2, -3. Usually we can use the empirical rule, like we did in the previous example, to help us determine the area of a shaded region under the curve, and that's if it falls specifically on those standard deviations. But we have a table that will allow us to more accurately find the area of a shaded region under the curve, called a z-table. So if you look at the next 2 pages of your notes, that will be table A. I'll refer to that often. Hey, look on table A. And those will give you z-scores. You have that in your formula sheet. You get to use that from -3.4 to +3.4. And the values in the table are your probabilities, which are the areas below the z-score. So we need to write that somewhere. Let's write it over here. So probabilities are the areas below. Remember, below means left. And so I'm going to go over there and just show you what the table looks like before we do the problems. So here you have the first page of that table. This is table A. And you look at the picture of this density curve and you see a z-score. And the values in the table refer to the left. So it's the probability lying below the z. Anything below the z is to the left. And so if you were given something above the z-score, you just need to subtract that area from 1, and that'll give you your probability or your area. And here's the positive z-scores. Going back to our examples, and there's several, just so you have some examples. Shade the appropriate region on the graph and use the table to find the area. So the first one is z is less than 0.58. So let's label these diagrams first of all. So we're going to do 0, 1, 2, 3, -1, -2, -3 for all of these. And then we want to find 0.58. So it's going to be over here somewhere. And so what you do is you sketch it, draw a line, and z less than 0.58 would be right here. So this is the area we're interested in. And you know it's going to be more than 50% because half, right at 0, it's 50%. So in order to figure this out, you go to your table and you find 0.58. So this is how we read it. Okay, it's positive, so go to the positive side. And you go to 0.5, so right here. and then you go all the way to where you see 0.08, which would be right there. So the answer is 0.7190. So make our decimal, and this is the area, and so that's the area, or you can say 71.9%. Same thing, referring to the same thing. All right. So another AP exam requirement, draw a diagram, label z-scores, and shade. Draw, label, z-scores, and shade. All right, let's do the next one. Z less than negative 1.10, so 0, -1. Oops, that's a positive one. What I was thinking. Okay, and then negative 1.12 is just a tad to the left. Oops. Maybe not that much, but it's okay. They know what you're talking about. I know what you're talking about if you're shading the correct area. So we go to the negative z-score. So negative 1 would be, negative 1.1 would be right there. And then go over to 0.02. And the area is 0.1314. Or 13.14%. Okay, let's do something a little bit differently. So shade the appropriate region on the graph and use the table to find the area. Again, 0, 1. I think on your homework, you might have to, oops, I'm glitching or something. There we go. All right. So right here, 0.26 would be around here. So you're going to find this area. But remember, the table values are to the left of that. So you are going to have to subtract. So the total area is 1 minus the area below 0.26. So what we want to do right now is go find 0.26. So here is 0.2 and then so that's 0.6026. Now, if you wrote that down as your area, you're basically just telling someone that this is your answer. But that's not what we want. We want it to the right. So we don't want to just get the values from the table. There we go. It's being really picky today. So we want to do 1 minus that value, which I just mentioned, which was 0.6026, and that'll give you an area of 0.3974 or 39.74%. This should make sense. If we did the other, you know that is not 60% because it's to the right of the halfway point. So just got to be aware of those kind of things. Does your answer make sense? So next one. Okay, over here, we want greater than negative 1.58. So right here is like halfway. So we want this shaded region. So that definitely is going to be more than 50%. So we are going to do the 1 minus because we want anything to the right. So let's find negative 1.58. So negative 1.58 right here, 0.0571. So that would give us 0.9429 or 94.29%. Okay. Shade the appropriate region on the graph and use the table to find the area. So this one's a little bit different. Let's label. Okay, this one I want to spend a little time on. So negative 1.19 would be right here. 0.26 would be right there. So we want z-scores greater than negative 1.19 but less than. So this area in between. Well, how in the world do we do this? So here's what I want to show you. So z less than 0.26. So if we're looking just at this part right here, it would be everything to the left of this value right here. So it would be all of this, and color it in blue. All of that. Now, z greater than negative 1.19 would be everything to the right. So, or I'm sorry. Yes, it would be everything to the right. So what we want to do is we want to subtract, because we want to first find the area of z is less than 0.26 because it covers everything to the left. And then we're going to find the area for z greater than negative 1.19. Actually, that would cover this little portion right here, because remember the z-scores are to the left. So I kind of said that wrong, and I'm so sorry. So for z greater than negative 1.19, we would determine what that is, because we want the area below the z-score, and that'll give you this middle portion remaining. So first things first, so let's write this down. Find area for z less than 0.26. Step 2, area for z greater than negative 1.19, and we already know some of these values because they are, that one isn't up there, but the 0.26 is. And then 3, subtract to find the shaded region. I remember doing this in geometry when you had to find area of some curve, you had to subtract. Okay, so the z-score for negative 1.19 is negative 1.1 is right here, and 9 would be all the way right there. So 0.1170. And then, so I'm going to write that down right here, I guess. Okay, and then for z less than 0.26, so remember, we can find that information right here. So it was 0.6026. Subtract, and that'll give you the z-score of 0.48, or the area of 0.4856. We'll do this one really quickly. You're probably thinking, well, why do we have to do so many examples? Well, just so it sticks in your brain. So the right side, z less than 2.09. So here's 2. So less than that would be everything to the left of that. And z greater than negative 0.58. Right here. It would be everything to the left of that, and then what's remaining is in the middle. So you take all the stuff left of this point, shade it in. You take all the stuff over here, shade it in, and you're remaining with the middle region. You don't need to shade it in because you know this is what they're asking for. So the area z less than 2.09 is 0.98. 0.9817, and you can see that because it's almost the whole density curve, minus 0.2810, and that equals 0.7007. Right? Using the table to find z-scores. Well, what if you have to find the z-scores and they give you the area? Because that's what the 20th percentile means. That just means 20% below. Remember what percentile was, at or below a certain value. And so what you want to do is find a z-score with an area closest to, find area closest to 0.2000, because that's 20%. So we are going to go to our z-score table and do a little searching here. So if you look towards the bottom, this looks like it's going to be closest to 0.2000, and that is negative 0.84, because negative 0.8 right here, and then reading the vertical column, that would be adding 0.04, so that's negative 0.84. Okay, and if they're asking you, well, explain your thinking. So here's 0, here's your density curve. It's kind of a really poor density curve, but whatever. And then you want, say this is negative 1. So negative 0.84 is going to be right here, and you're finding this area. Right, 76th percentile, so that's 76% below. Let's sketch the situation first. So that would be right here. That would be the 76th percentile. So below that, we want this. And find a z-score with an area closest to 0.76. So let's find it closest to 0.76. So we're going to have to go to the second page. And my eye catches this number right here as being the closest. So that would be 0.7 plus 0.01, so 0.71. And this is your z-score, not your area. All right, so the next two pages were just the tables. And let's finish up doing 2 examples. Okay, in the 2008 Wimbledon tennis tournament, Rafael Nadal averaged 115 miles per hour on his first serves. Assume that the distribution of his first serve speeds is normal with a mean of 115 miles per hour. I'm just underlining this so I know I can label my diagram. And the standard deviation of 6 miles per hour. About what proportion of his first serves would you expect to exceed 120 miles per hour? So this is the 4-step process that I mentioned we were going to do so much of in second semester. The state plan do conclude. Nadal's first serve has a normal distribution with a mean of 115 miles per hour and a standard deviation of 6 miles per hour. The question, what we're being asked is, find the percentage of serves that exceed 120 miles per hour. It's the last sentence. So the first thing we want to do is label these values. And notice they're already sketched in for you, 1, 2, and 3 standard deviations within the mean. So this is 115. Okay, and then you are going to add 6 to each score because it's standard deviation is 6. So 121, 127, 133. To the left, subtract, so 109, 103, and 97. Please don't make mistakes in subtracting. Use a calculator if you have to. You just don't want to mess up on simple stuff like that. Okay, so the graph to the left shows the distribution with the area of interest shaded. Well, I have not done that yet, so we want exceeding 120 miles per hour. So because it's not right at 121, we can't use our 68, 95, 97 rule. And we want exceeding. So what do? We want to find the z-score for, we want to use our z-score standardized formula because we need to standardize it. So z-score, because these are scores. If you remember the formula from the first day of the chapter, the z-score is equal to the value, and the value in question is 120 miles per hour, minus the mean, and the mean was 115, divided by the standard deviation. The standard deviation is 6. So if you do the math, that equals 5/6, which is 0.83, where the 3 is repeating. So now look at your table and find the area corresponding to 0.83. Okay. So here's 0.8. So it'd be 0.7967. But remember that doesn't give you this value. You need to subtract from 1 because it's to the right. So always got to remember, anything shaded to the right, you must subtract from 1. So 1 minus that 0.7967, and that would be 0.233. So answering the question, about 20.3% of Nadal's first serves travel faster than 120 miles per hour. Let's do our last question, and then you're going to do 2.2C and D on your own, which is using the graphing calculator. And I'll walk you through all that with a separate lesson. About what proportion of his first serves are between 100 and 110 miles per hour? So for this state, Nadal's first serve has a normal distribution with a mean of 115 and a standard deviation of 6 miles per hour. Find the percentage of serves are between 100 and 110. So here's 115. Because we want everything to the left of it, because that's 100 to 110, we don't need to sketch the right side. So 115 minus 6 is 109, minus 6 is 103, minus 6 is 97. Okay, and let's sketch between 100 and 110. So here is 100 right in the middle, and 110 right there, more or less. So we want this information. So this is where we're going to have to subtract. Find the area for, we'll find the z-score for 109, find the z-score for, 110, find the z-score for 100, subtract, and so on. So let's do the z-score first for 110. So the z-score is equal to the value minus the mean divided by the standard deviation of 6. Do the math there. That's 5 or negative 5/6, which is negative 0.83. Okay, and then go to, we don't even need to know. We know that that corresponds to 0.2033. So I'm not going to go to the table. Okay, now find the z-score for the lower bound, which is 97. All right, I don't know why I say 97 for 100. Sorry. Clearly states 100 to 110 miles per hour. So the z-score for 100 is equal to 100 minus 115 over 6. So it would be negative 15 over 6. which is negative 2.5. And if we look for negative 2.5, it is right here, 0.0062. So to find the area, you're going to take the upper bounds area minus the lower bound area. That'll give you 0.1971. And that makes total sense that that could be that percentage. So about 19.7% of Nadal's first serves travel between 100 and 110 miles per hour. Well, tomorrow you will know that you can do this kind of stuff with a graphing calculator to make it easy. I like the visual stuff when you're first learning it because it really makes you see it. So these are the notes for today. Have a great day, stat students.